Okay, so today we're actually going to look at using these vectors, vector addition or whatever, for some actual applications. We broke down the vectors into components and we added and subtracted vectors back on, was it Wednesday, I guess is when we met. Today we're going to look at solving a problem with them. Simple problem we might have might look like this. Here's a wall, and we have a shelf hanging on that wall. And to support that shelf, I can't draw a chain, so I'm just going to draw it as a line. We have a chain or a cable or whatever supporting that shelf. I'm going to make this here 24 inches. Actually, I'm going to make, yeah, we'll leave it like that. That'll work. Now I'll make the length of this chain here 36 inches. And I am going to put a weight here, and the way we do that, rather than drawing and then we just put an arrow pushing down. Let's say this needs to support a, let's have it be a 120-pound weight that shelf has to support. What are the forces there? There's two things that are vital here. There's the chain itself to make sure that can handle the force that's being put on it. And then there's actually the wall, making sure there's adequate support at the wall. So, we're looking at this point right here. What has to happen? Well, I'm going to draw, it's called a free body diagram. Where I'm going to draw that point and all the forces that act on that point. So here's that point. Again, that's this point right here. I have that 120 pounds pushing straight down on it. I have the chain. Of course, that's a known force. I'm going to draw my unknown forces in a little bit different color. I have my chain coming out this way. I'm going to call that force, force A. And then I have the wall pushing out. And usually it's the wall is pushing out along here. I'm going to call that force B. Now, first thing I need to know is what angle is formed here. And that is, since the chain goes off in that direction, the force has to go along the axis of the chain. So I can find it from this angle here. This forming a right triangle. This is 24 and 36. What trig function is going to describe that angle? Hypotenuse, and what's this side? Adjacent. So adjacent over hypotenuse is cosine. So that's going to be an inverse cosine of 24 over 36. It's 48.19 degrees. From here, we have two options. We can break it down into components, or we can use something called Bose notation. Kind of ironic that he's not in this class this semester. Huh? So Bose notation means we start at we pick one of the forces, usually a known force. I'm going to use that 120 pounds going straight down since that's the only known force. So I'm going to pick a starting point. I'm going to use that force going down, 120 pounds. And the length of that vector, geometrically, should be scaled to that 120 pounds of force. Now if I go around here counterclockwise, we usually travel, the next one I would run into is force A. Should have drawn this on the other side. Force A takes off at that angle going this way. I'm actually going to do it in a lighter gray. This angle here was the 48.19 degrees. Which means this angle here has to be 41 point, yeah, the complement, 41.81 degrees, right? And then force B is perfectly horizontal, so it's got to go back exactly horizontal and get us back to that starting point. So what I have here, now I'm going to draw it in darker. This is force A. This is force B. And the geometric lengths of them actually do work out. So I have that right triangle where I have this side of 120. That's the adjacent side to my 41.81 degree angle. Let's find A. That's going to be a cosine of 41.81 degrees is going to equal 120, that's the adjacent side, over force A. So I put this over 1 times 120 divided by cosine of 41.81. So 1 times 120 is just 120. Divided the cosine of 41.81. 160.996 or 161 pounds comes out to be. What's that? Yeah, I don't need to put the degree sign on it. Yeah, when I put it in cosine, the fact that my calculator is set to degrees, it's okay. Now make sure your calculator, we set them to radians for the last unit, so make sure you got it set back to degrees. It should just be blank on the screen instead of saying rad. Did you say rad yet? Okay, radians. Okay, so you're good if it says DEG, or if it says nothing, you're good. Okay. So that's 161 pounds. Now we need to find B here. B would be the opposite side of our 120, so that's tangent of the 41.81 degrees equals B is the opposite side over the 120 pound adjacent side. Put this over 1, so it'll be tangent of 41.81 times 120 divided by 1, so of course we don't have to divide by 1. Tangent of 41.81 times 120. 107.33 pounds. So what that's telling us is this chain here has to be able to support at least 161 pounds. The wall here has to be able to support at least 107.33, about 110 pounds pushing out. Because it's going to have that much force pushing back into it. Does that make sense? That's a lot longer conversation. Yeah. Now here I had the weight sitting way out on the end of the shelf. Most of the time it doesn't work like that. Yeah. A much more efficient way to do it exactly. You know the chain is strong enough to support it. Yeah. So let's say we got 24 inches and 36 inches again. And now we're going to put our 120 pounds right in the center. Pretend that's right in the center. What changes is this. This acts as a beam. Now, we're not going to get into moments in here because it's not part of the course. What happens when you have a weight sitting at the center of a beam, it's exactly the same as if you had just a plank set across two sawhorses. If I put 120 pounds here, how much weight's going to go to each? Yeah, half of it's going to go each way. So that's the same thing here. We can replace that 120 pounds with 60 pounds here and 60 pounds here. What that does is now that this is half of what it was before, well, that chain only has to be able to hold 80.5 pounds instead of 161 pounds. And the wall only has to be able to push out with like 54 pounds instead of 108 pounds. But there's an added strain here. The wall has to be able to lift up, has to hold up 60 pounds because there's a weight pushing down on this end now, and in the other example there wasn't. Now in an example like this, two of the things we were dealing with were vertical and horizontal. We had, the weight going down was vertical. This piece was horizontal here. So that made life a lot easier, and it made a right triangle for us. We often won't have a right triangle. Nope, the angle on the chain was completely determined by those two lengths.
Okay.
That's where we got that 48.19 degrees.
I just didn't know since we had vertical horizontal if there was something like that.
Nope, no, that was just determined by the dimensions. Let's say we have a post here. And this post has a wire that's pulling with a tension of 800 pounds. What do you guys have you guys done any elevated wires? Have you guys talked about tension on elevated wires? Okay. I know most of them are up around 400 or 500 pounds minimum, depending on how far they're spanning. We're going to put a guy wire on that. We need to figure out how much it's going to have to support. How much tension has to be on that wire. This wire, let's say this is up 30 feet, and this is going to be 18 feet back from the post. So we have to exactly counteract the 800 pounds. If I have too much, it's going to pull the post back this way. Too little, the post is going to start to go the other way. So anyway, you need to find angles here. I'm going to find this angle right here. How do I find that angle? Opposite and adjacent. That's going to be a tangent. So it's going to be the inverse tangent. Which one goes on top? 18 over 30. Very good. 30.96 degrees. In reality, I'd probably just call it 31 because it's really close. So anyway, what we have now from this point right here is we got the 800 pulling out. This is going to be pulling this direction. Where else do we have a force here? From the pole, exactly. Think of our components. This is strictly horizontal, right? There's going to be a horizontal component here that counteracts it. Well, that gives us a vertical component. The post has to lift up to counteract that vertical component. One of the basic rules of vectors and something called equilibrium is the sum of the forces equals 0. To do that, we generally break it down to the sum of the horizontal forces. F with little h is forces horizontal equals 0. And the sum of the vertical forces equals 0. So here, this is the only purely horizontal force in the system is at 800 pounds. So this horizontal component has to be 800 pounds. But in order to achieve that 800 pounds, because of the angle of the cable, obviously the cable has to have way more than 800 pounds of tension. The angle here was the 31 degrees. That's going to be this angle here, 31 degrees. I have 800 pounds here that I need of horizontal force. What would the vertical component have to be to go with that? Well, that's going to be a tangent. Tangent of 31 degrees equals 800 pounds over that vertical component. So 1 times 800 is 800 divided by the tangent of 31 degrees. So 1331.4. 2 pounds. So that's what that vertical component is. That means that the pole over here has to be pushing back up with 1331.42 pounds. The total force on that cable then, a couple ways I could do it. I could do a squared plus b squared equals c squared, but that requires me to use a rounded measurement. So it's probably easier if I just use sine of 31 degrees equals 800 pounds over the total. I'm going to call m for magnitude. So 1 times 800 is 800 divided by the sine of 31. 1553.28. So that cable has to be able to hold a minimum of 1,553.28 pounds. So probably use a 2,000 pound cable on there because you're looking at over time any corrosion, any fraying of the strands. Your safety margins on those cables usually involve a percentage of the strands that can break before the cable would fail. And usually it's surface strands that they calculate how all of the surface strands, so the strands that are within so many layers of the surface of the cable, which the bigger the strands are, the bigger your safety margin is. So let's say you got a cable like this, you got strands. And obviously they weave in and out, but they're only at the surface. At one spot, there's only one layer at the surface.
Would this be the same stuff they use on bridges?
Yes.
Okay.
Yeah, very much so. Like bridge structures and stuff like that, there's a percentage of the cross-sectional area of the beam. It's the same type of thing. If you have an I-beam, like something like that, there's a cross-sectional area there. Generally just break it down into rectangles like this. Thank you. And you lose some in those corners, but you can get a pretty good approximation of the cross-sectional area. And there's a percentage of that cross-sectional area that can be corroded. So in other words, the rust can go so deep before it causes a problem. Now look here, let's say that this is a 1-inch cable, 1-inch diameter cable. And these strands, let's go 1/32 of an inch strand. So the area of one strand, well, let's just do this. Let's do the area of the whole cable first. So that's going to be the area of the whole cable, pi times 0.5 squared. So come on, 0.785 square inches. So a 1-inch diameter cable is 0.785 square inches of cross-sectional area. If we lose a 32nd of an inch here, all the way around. So let's say we're only allowed to lose the outer layer of cables, the outer strands. Well, that's now a 32nd of an inch on each side. So the radius is decreased by a 32nd of an inch. So what is 0.5 minus 32nd? 0.46875, that's what I thought. Squared. .690, we're going to call it, inches. If I take that 0.690 and I divide it by the 0.785, That's down to under 88% of the area. So I've already lost 12% of the area by losing one layer of strands, of cable strands. So it doesn't take much to take a significant. So this cable, if I lose that outer layer of cable strands, has lost almost 13% of its strength. If that makes any sense.
What are the chances of them all breaking in a perfect circle around it like that? When did you break some on the inside of it?
Yeah, you're absolutely right. The chances are they're not going to break in a perfect circle, but that's just they use the exposed strands. They figure those are the ones that are going to corrode and break first, and they won't all break in the same spot. And that's one of the reasons why they're woven together. And this is where it gets complex. Yeah. By being woven together, it limits their ability to slide past each other. If they were just like straight strands in a bundle like this, if this strand broke here and this strand broke here and this one broke here and the next one broke here, they'd just be able to slide past each other and come apart. Being woven, those aren't intentionally sine waves, but by being woven, if this strand breaks here and this strand breaks here, if they're far enough apart, those two breaks don't affect each other. The weave of the cable holds it together. So there's a minimum distance depending on the weave pattern and the material of the cable and a bunch of other stuff. There is a distance if those breaks are in separate strands are more than a certain distance apart, they don't compound each other. They don't add to each other.
Okay, so the cable basically, if it's flexed or stretched, will tie the cable together so that it can't move.
Yes. So let's say all of the strands break, but at different spots far enough apart, the cable will still hold together because they won't slide past each other. Now there's a force that's required to get them to slide past each other. If it, it's called a critical force. If it exceeds that force, then they slide past each other. But still, it's so usually what they look at is breaks per certain length. That varies on the type of cable of how big that length is. That they can't have more than a certain number of breaks, broken strands per that unit of length. Because if they're further away than that, they don't affect each other. It's actually kind of, like I said, it gets to be pretty complex. Well, what if I have vectors that are not like nice and neat like that, coming in at straight? So all horizontal and vertical. I'm trying to think of a good example and I'm blacking out. So we're just going to do one. Yeah. Hey, I was an engineer for 6 years before I realized they were never going to let me drive the train. What we're going to look at is actually a roof truss here. So we're going to say this angle here, I'm just going to keep it simple. I'm going to call that 26 degrees. And this here I'm going to call 70 degrees. And let's say we know that this truss is holding 2,000 pounds total. So that means there's 1,000 pounds on each end. Does that make sense? So it'd be another 1,000 pounds over here. Well, looking at this end here, analyzing the vectors here are still pretty simple because our force is vertical and the bottom chord is horizontal. So if I'm looking at that point, I've got 1,000 pounds coming straight up. I have whatever that horizontal is, and then I have this here coming at that angle, the 26-degree angle. Well, I know this has horizontal and vertical components. I drew them in that direction because I knew that this vertical component has to counteract 1,000 pounds, right? This has to be 1,000 pounds going downward. If this is 26 degrees here, this is also 26 degrees. So I can find that component there. That component there is off a tangent. Tangent 26 degrees is 1,000 over whatever that is. I'll just call it x for now. So 1 times 1,000 is 1,000 divided by the tangent of 26 degrees. So 2050. So 2,050 pounds. That being horizontal, the only way that can counteract that is this piece has to have 2,050 pounds of force on it. Make sense? So that means this thing here has to point this way because this is the tail, this is the head, right? So I would combine the 1,000 and the 250. I'm just going to do it the easy way. I know I'm using rounded numbers, but so 2281. 100 pounds, 2,281 pounds is what's on that piece right there. Well, the reason I did that is I want to get to this joint right here. Now, one of the funny things about a truss is it's pushing out here, it's in compression, it's going to be pushing out there as well. It pushes out on both ends. So at that point, I have that 2,281 pounds coming in at that 26-degree angle. I have a mystery force going out here at that same angle, and I have another mystery force coming in here that makes an angle down here 70 degrees. I know this has components of 1,000 pounds and 2,050 pounds. I found that from up here in this last joint. This one's going to have components. This being 26 degrees. This one's going to have components. I'm going to make the assumption that this one's pushing that way. That one's, we call it compression. This one, we're going to make the assumption that it's in compression. Mainly because the horizontal component of this one would be hard-pressed to be large enough to counteract that 2,050 pounds there. So now we've got some issues. If I call this force A and this force B, this, of course, is the horizontal component of A. This is the vertical component of A. This is the horizontal component of B and the vertical component of B. We know from that sum of the forces, sum of the horizontal forces, we've got 2,050 pounds here. I drew it so that AX is negative, so I'm going to do minus AX. BX is also negative, minus BX. That has to equal 0. Has to add up to 0. AX is going to be A times the cosine of 26 pounds, or 26 degrees, right? That's cosine. So I'm going to rewrite this equation here. 2050 minus AX is going to be A times the cosine of 26 degrees. BX is going to be B times the cosine of 70 degrees. It has to add up to 0. Because of time, I'm going to do some fancy algebra here. I'm actually going to add both of these to both sides of the equation so they cancel out over here. So I've got 2050 equals A cosine 26 plus B cosine 70. Does that make sense? Yep, they're both negative, so I added them to move them to the other side and make them positive. Now I've got the sum of my vertical forces. Well, I've got the 1,000 pounds going up is positive, so that's 1,000 pounds. AY is going down, so that's minus AY. by is going up, so plus by. That has to add to 0. Well, AY is A times the sine of 26 degrees. BY is B times the sine of 70 degrees. That's equals 0. So now I'm going to add this one and subtract this one to move them to the other side. So I have 1,000 equals A sine 26 degrees minus B sine of 70 degrees. So now I'm going to fill in some numbers. Sine of 26, 0.4384. That's 0.4384A. Sine of 70, 0.9397. B. Do the same thing here. I got my 2050 cosine of 26. 0.8988 A. Cosine of 70. 0.3420 B. And there we have a system of equations. You guys solved systems of equations last semester? Like if you have 3x plus 5y equals 17, and 2x minus 3y equals 1, find x and y. Well, this is just a system of equations. Might be slightly uglier than any of the ones you've solved, but it's a system of equations. Rather than, here if we were going to use elimination, we'd multiply this top one by 3 and this bottom one by 5. So you got positive 15 and negative 15y. With these ugly decimals, that's not easy to do. So what I'm going to do is I'm going to get, since I have a negative here and a positive here, I'm going to get rid of b's. But rather than multiplying, I'm going to divide. I'm going to divide this top equation by 0.9397. So 1,000 divided by 0.9397 is 1,064.17 equals 0.4384 divided by 0.9397, 0.4665 A, and then of course divided by itself, that's just going to be a negative 1b. This one I'm going to divide by the 0.342, right? So I got 2,050 divided by 0.342. $59.94.15. 0.8988 divided by 0.342. 2.6280 or 2.6281. A, and this is just plus 1b. Now the b's will cancel out. So that's 7,058.32 equals 3.0946A. So I'm going to divide by the 3.0946. So 7058.32 divided by 3.0946. 2280.85. We're just going to call it 2281. is the force on A. So it's saying up here, which one was A? That was A. So still 2281, huh? So that force stays 2281. So we can find the force on this one by going back and substituting that back in the equation and solving. Make sense? Cool. I'm not going to make you guys go quite that far, just so you know. We're going to be able to look at this geometrically. If we have a point, we've got 2,281 pounds coming in like this. An unknown force here and an unknown force here. From our known point, we're going to use Bose notation. 2281, that's at that 26 degrees. Going on counterclockwise, we hit this one. It goes up here, that's at 70 degrees here, right? Then this one has to bring us back down somehow. Well, the angles are off, it's not going to work. This one ends up having to be 0 is what happens there. Okay, I think you guys have had enough for the day. I'll have you try these and we'll go over them some more tomorrow. I'm feeling I'm not done top of my game today either, so I don't think I'm explaining it as well as I could either. But in that packet, page 393 through 395, can somebody double check to make sure that's in that packet, or do I have to grab another worksheet? I think it's in that packet. Oh, nope, there is another worksheet here I gotta give you. Start about combining vectors and their diagrams. Like I said, I fully anticipate we may have to go over this a little bit more tomorrow.
I don't think I'm gonna be here tomorrow.
Okay.